Here we have a more organized summary of the results for impedances and phasors in general. So technically the definition of impedance up here is the phasor voltage divided by the phasor current of whatever element you're talking about. We have the formula for the impedance of the resistor. Z is just R. For inductor, Z is equal to J omega L. And for the capacitor, you can either write this as negative J over omega C or 1 over J omega C. And it turns out that once we turn everything into these phasors, these impedances behave identically to resistors. So that means if you have them in series and you want to find the equivalent impedance, you just add them up. If you have them in parallel, you do the standard parallel rule for resistors. And it's even possible to use Y delta with these things. But you can stop for a second and think about how awful Y delta would be with imaginary numbers running around everywhere. So I'm not going to make you do that, but it does work. It gives you the right answer. And so basically, once we turn our circuits into phasor versions of the circuits, we're actually going back to chapters 3 and 4. Right? You can use node voltage, you can use mesh current, you can use Thevenins, you can use superposition, you can use all of the things that we learned about handling just resistor circuits, but now they're going to work with resistors, inductors, and capacitors as long as you use phasors. So phasors is going to make our lives so much easier. We can go back to using all of our old stuff. On the other hand, if you never learn chapter 3 and 4 well, then you're going to have even more trouble right now on this. So if you need to brush up on, mesh current, node voltage, Thevenin, any of that source transformation, any of that stuff, you're probably going to want to review because you're going to need it for chapters 9 and 10. Okay, so